We are discussing the simple pendulum in uniform acceleration. So just for a quick review, this is your pendulum, and when it is here, it is in the equilibrium position, that is this theta angle is 0 with the vertical, you can say. Now at this position there is a tension in the string, then there is, if this is the angle, then we make a vertical, so this will be theta. So this is the weight, that is mg. Now this is the horizontal component mg cos theta, and this is the vertical component mg sin theta. So T is opposite to mg cos theta, and mg sin theta will be, we'll see how it works. There will be a force. So this Ft on the radical axis we are talking about, this axis, the Ft, this force T will be equal to mg cos theta plus one more force, which is mv square by L. L is the distance. Okay, this is the force. Two forces are there, we added. Equilibrium, as we said, theta equal to 0, and this is nothing but the centripetal force. When the ball reaches its maximum amplitude, that is this one amplitude, the velocity will be 0. So this Ft will be simply mg cos theta. Velocity, if you put here 0, it will be just mg cos theta. So Ft will be at the maximum amplitude. Now in the tangential axis, this was the radial axis. Now on the tangential axis, this axis, we have mg sin theta, and mass and acceleration is going like this. So these are opposite. Okay, by Newton's second law, this F net will be, if this is minus mg sin theta, this will be ma, or if this is minus ma, this will be mg sin theta. So what we get, a equal to minus g sin theta, and if you just consider this theta, see this is theta. So if I take a sector like this, theta, so this can be, L equal to r theta. We know about this for a circle. So this S, or this S will be, if this is say L, and we have this as theta, so S will be theta into L. So this S will be equal to, or theta will be S by L. This is arc length formula. We can put theta as S by L, and we know for very small angle the sin theta can be taken as theta. So here theta is simply S by L. We will put S by L. So this will be G into S by L. This is the value, and you can find omega is equal to under root G by L, and time period is always 2 pi by omega, that will be 2 pi under root L by G, right? So we'll see about that. The key equation will be this, T equal to 2 pi L by G, which I wrote here, L by G. This is our final. So this is a quick review. A simple pendulum in uniform acceleration, the key equation, as we just said, it will be T equal to 2 pi under root L by G. A very simple case will be the pendulum, a simple pendulum is still or at uniform motion. So whether it is still or it is in uniform motion, moving like this in uniformly. So a simple pendulum is hung. That means whenever we are talking about still or uniform motion, we are saying that acceleration is 0. There is no acceleration. So a simple pendulum, let us take a question, is hung on the ceiling of a still bus. What is the period of the pendulum? What it will be? Will it be T equal to 2 pi L by G? So a simple pendulum is hung on the ceiling of still bus. What is the period of the pendulum? The general idea which we imply here is just we consider the period equation of simple pendulum, which we know by now, T equal to 2 pi L by G. Now what is this pi? Pi is a constant, that is 3.14 or 22 by 7 you can take. And the length of the rope, let us say to be L. This is also a constant, so the only variable that can be changed in the uniform acceleration is the gravity. Okay, you can say effective gravity acceleration. So in this question, since the bus is not moving, bus is stationary, the only two forces exerted on this ball is the gravity of the ball and the tension of the string. The G, that is the gravity, is directly equal to the gravity acceleration, so this will be G only. Effective gravity acceleration will be equal to G only. So the time period will be simply T equal to 2 pi L by G, or given by this equation, right? This is T, tension, and mg. So T, mg, the time period will be this equation. Then we have inertia. Just recall what was inertia, inertial force and inertial acceleration. The ascending or descending elevator in real life. So if we have an elevator like this, we know that the people will feel heavier or lighter in an ascending or a descending elevator. You might have felt that. In physics, what we say that the apparent weight is lighter or smaller. The apparent weight is lighter or smaller than the real weight of the person. The idea which can also be explained by inertia, which is basically meaning that there is a force, we call it as inertial force, of which direction is always opposite to the direction of acceleration. Force will always be opposite to the direction of acceleration exerted on an acceleration or accelerating or retarding body. Retarding means deaccelerating body, right? So if we have this situation, we have acceleration this side, then the force will be this Fn, that is net force, will be in this side, and mg will always be downwards. See here also mg is downwards. So what this Fn will be? Fn will be, because it is inertial force, will be ma. So ma is this side, ma plus mg. This gives you ma plus mg. So force net will be ma plus g. That's mg. Because Fn is the apparent weight and g dash is nothing but, this g dash is nothing but effective gravity acceleration. Now when we are moving down, so what will happen? Now the force will be equal to mg. Mg will be in this direction, and then the acceleration will be minus a, because we already know that there is a force in which direction is always opposite to the direction of acceleration. So force, if acceleration is like this, force will be like this. Okay, so this net force will be mg, and then because there is an apparent lightness in the weight, you can say mg minus ma, so it will be mg minus a, again it will be g dash. The acceleration or retardation or deacceleration bus in real life, what happens? When a bus driver brake hard to stop a bus, the passenger will jerk forward. It's similar to the ascending or descending of elevator. So in general, we will still apply the inertial force on this horizontal uniform acceleration. So the vertical direction, what will happen? See, this is the vertical direction. Force is here, Fn, and this is the mg. The inertial force is like this. Okay. Now this is the accelerating bus. So Fn will be always equal to mg. But in horizontal, this is the vertical direction. See, we are talking about now the vertical direction. So there will be a net force and mg will be like this. This is the vertical direction. Now let us take the horizontal direction. Horizontal direction will be, see, it is uniformly the bus is retarding. So the inertial force F will be this I, this is Fn, this is Fi. Inertial force will be m into a. A simple pendulum is hung on the ceiling of an ascending elevator in a uniform acceleration A. What is the period of this pendulum? Will you be able to solve this? See, it is hung on the ceiling of ascending. Ascending means elevator ascending, going up with uniform acceleration. So A is like this. What is the period? So let us see how do we solve it. The answer is t equal to 2 pi under root L by g plus a. What is the explanation? How do we get this? So we know that the ball in a simple pendulum will reach its equilibrium state when theta equal to 0. Okay. So at the equilibrium state, we have equation like this. See, this Ft will be equal to mg downwards and ma plus mg. Since the elevator is ascending, we have to consider the inertial force to meet the demand of Newton's second law. M, you can say, and what is the resultant acceleration? A plus g. So the effective g dash will be a plus g. So the period of this pendulum in ascending elevator will be t equal to 2 pi under root. We are adding g plus a here. A simple pendulum hung on the ceiling of a descending elevator. Now this elevator is descending. Uniform acceleration is a. What is the period of pendulums? We'll adopt the same thought here, logic here. The answer would be g minus a. What is happening here? This is similar to the question we just saw. We first analyze the equilibrium state of the ball in pendulum and then find out effective acceleration. So we can find that the equation, that is Ft, this Ft will be equal to mg and minus ma. This will be the effective. Say G dash will be effective G minus A because it is coming down. So G dash will be G minus A. So in the place of G, we put G minus A. So period of the pendulum in an ascending elevator will be T equal to 2 pi under root L by G minus A. So what we saw to find the period of a simple pendulum in certain uniform acceleration, there are few steps. First of all, just find the equilibrium state of the pendulum, that is when theta equal to 0. We find the force equilibrium of the equation of the equilibrium state. Then we analyze the acceleration of each direction. We compose the acceleration if necessary. Then find the effective gravity acceleration like G plus A or G minus A. Then finally we put G dash like this one or this one in the formula. This one formula. Now simple pendulum is in an uniform accelerated bus. So we have a pendulum also, and there is a uniform accelerated bus. So a ball is hung on the ceiling of a motionless bus by L meter long rope. The bus suddenly starts with a right acceleration A, right, meter per second square. Note that the acceleration A is much less than the gravity. A is very less. Find the effective gravity acceleration of the ball in the bus when time equal to 0, means initially. Assume that tan theta equal to theta, where theta is small. Find the amplitude and period of the ball. So what we are going to do here? See, first of all, we have to find the effective gravity acceleration of the ball in the bus when time t equal to 0. At t equal to 0, the bus has right acceleration, that is A. But the velocity of the bus is still 0. Therefore, the ball will reach its equilibrium state in this accelerated bus in that instant. So see here, this is the equilibrium position and this is the position where it will go. So let us see what all is going on here. Tension is here. We have the mg downwards, but we have theta here. So this will be what? This will be mg sin theta, and we have mg cos theta also in this radial direction. So what will be the ft? That is, it will be m, and what will be this? See, this is A, this is G. So if I say this is A and this is G, or you say this is A, what will this be? This will be under root A square plus G square. Okay, A square plus G square, this one. So this is A square plus G square. So what will be the force, mass into acceleration? Acceleration is A square plus G square under root. The total for the mass into acceleration will be this one. So Ft, this tension, will be m into under root A square plus G square. The effective gravity acceleration is this, we found from here. A ball is hung on the ceiling of motionless bus by L meter long rope. The bus suddenly starts with a right acceleration this much. Note, we have to note that the acceleration A is much less than the gravity G. Now we are taking the other part now. We have to assume we are taking the same question, tan theta equal to theta when theta is small. We have to find the amplitude and the period. Now we know that the velocity of the ball will be 0 when it reaches its maximum amplitude. That means here it will be, this is the maximum amplitude, the velocity will be 0. So when the bus starts, the ball reaches its equilibrium position, that is theta equal to 0. This theta is 0, this position. So what will, let us see this. This is the bus has not started, and this is the equilibrium state. What this A will be? We know that this by L equal to R theta. So theta is theta, R is L here. See, this is L here, L theta, and L is A here. So A will be equal to L theta from simple R formula. Now theta can be taken as tan theta because it is given. You can take tan theta as theta and theta as tan theta. But what is tan theta here? See, this is tan theta. Tan theta, if I made a triangle like this tan theta will be perpendicular by base. Perpendicular is MA, this base is MG, so MA by MG. MM cancels out, it will be LA by G. Since we already have the effective gravity acceleration, we just found it in the previous discussion just now. So this will be equal to T equal to 2 pi under root L by G, and 2 pi L by G will be equal to under root A square plus G square. After this, what we do, because this is simply the amplitude will be, as I said, amplitude will be at this position 0, and period will be this one, equal to 2 pi under root L by A square plus G square, this one. Okay, and this amplitude will be what? amplitude will be ALA by G. So simple pendulum, when it is in uniform acceleration, let us summarize. If it is going up, you get t equal to 2 pi under root L G plus A. If it is going down, L G minus A. And when we have this position, like it is going on a road and you have a pendulum with some certain acceleration, then t equal to 2 pi under root L by G square plus A square. See, the real line represents the equilibrium state. This real line is the equilibrium state. The dotted lines represent the maximum amplitudes. These are the maximum amplitudes. Okay. So this was the basic idea about a simple pendulum when it is inside your, say, elevator, or it is moving in some vehicle. Thank you so much. Take care of yourself.